Next, we have been able to cover both electric flux density, and also we have been able to cover the energy and potential, energy and potential, all in electric fields. Okay? So this has been vastly um, described using the Coulomb's law. This has been vastly described using Gauss law. Okay, and with this background, so we would be able to apply these concepts uh, in understanding the different uh, elements in the electromagnetics as well as electrostatics. So with this background, we shall start studying about the conductors, okay, dielectrics, and capacitance. Very important. The knowledge of electric field intensity, electric flux density, energy, and potential are all very much essential in understanding the um, characteristics of the conductors, dielectrics, capacitances. Okay, so how the current flows in each of the uh, elements like conductors, dielectrics, and all. Okay, those things we shall discuss in detail here. Okay, so let us start with basics. So with the background of the charge, with the background of electric field, with the background of electric flux, and with the background of energy and potential, so we should be able to understand. So what is electric current? What is electric current? And what is density? Current density, okay? And how this is related? Is electric current and current density in a given material. Okay? And so, what exactly, how the current behaves, how the current behaves in a given system. Okay? So, these things are very much essential in understanding the arrangement of different or properties of different materials. For example, it might be a conductor, it might be a dielectric, it might be an example for dielectric is nothing but capacitor. So like that. So these things decides the basic properties of any element, and you can understand these concepts under different conditions. For example, it can be a static condition, it can be a dynamic condition, so it can be a, uh, a different conditions, which can be homogeneous medium, or it can be a heterogeneous medium. Okay, like that. So you can study different properties of materials with this knowledge. So you should know, or you should be able to explain what is current and what is current density, and that is nothing but in terms of charges. We have to discuss those things in terms of charges. Okay, so the charges and all we have discussed in detail in the um, uh, preceding chapters. Preceding chapters. Okay, so those things we will not be recalling at length. Just here and there we'll be using the concepts what we have studied. Okay, so firstly is nothing but you should know before knowing the definition of electric current, you should know what exactly a conductor is. Conductor is nothing but um, made up of metals such as copper. Example is copper, aluminium. Okay, so these things will have some free electrons. Okay, these free electrons. So when subjected to some external energy, okay, these things having free electrons, when subjected to some external energy, okay, so what would happen? So the electrons will move from the negative to what positive. That means this is a conventional flow. Okay? The actual flow of electrons. So that passes through like this, reaches the positive terminal. But what we have studied so far, that means the electrons will flow from higher potential to what low. That means current will flow from higher potential to what low potential. So we have assumed that this is a higher potential, this is a lower potential. So this is the basic assumption what we have done. But actual electron flow takes place from this point onwards to this point onwards. Okay. So the free electrons move radially, so move readily under the influence of some external force. That is but we have to create a field. Okay. So that means it constitutes the flow of negative charges. Okay. Flow of the negative charges which flows from the negative terminal to the positive terminal. So, but we tend to assume that the flow of charges takes place from the higher potential to lower potential, so plus to minus. But originally, it happens like this: electrons will flow from the cathode to anode, like that. Okay, so this constitutes some flow of charges. So this flow of charges, this flow of charges, so and the rate of flow of charges is nothing but electric current. So what we can define electric current as, so it is nothing but the rate of flow of charge. That means the amount of charge which is flowing across a given cross section. Okay, given cross section of any conductor that is to be under a given period of time, which is called as the dielectric current. So that is called as electric current. Okay, so basically you should know there should be what flow of charges, and it should happen through a cross section of the material, that is nothing but conductor, and you should have some time units to measure. So these things defines the electric current, that is denoted by I. So that is basically nothing but delta Q by delta T. So delta Q is nothing but the amount of charge that is flowing through the given cross section in delta T seconds. So this is nothing but your uh, electric current. So rate of flow of charges, it is nothing but electric current. Sometimes it is also written as del Q by dt as time tending to what or cross section depending on the okay. So steady. Next is what exactly do you understand by steady current and instantaneous current? So steady current and instantaneous current. Okay. So steady current is nothing but if this rate of flow of charge is constant. The rate of flow of charge is constant with the time, then current is said to be steady current. So if it is varying with the time, so if it is continuously varying with the time, So it is constant, okay, and it is varying, varying with time. Then you can find the instantaneous current as time tending to infinity. Okay, so this is nothing but your steady current, instantaneous current, and the definition of the electric current. Okay, so you should understand that for the current to flow, you need to have some variation of charges with respect to time. So where you want to find the amount of current flow. Okay, so that is what the basic definition. And we can also discuss about the steady state current. That is nothing but steady state current. That means if the variation of charge flow um, has some definite um, um, value and definite direction with the perfect periodicity in both directions, then it is said to be what steady state current. That means, for example, if you take an AC alternating current like this, so what happens here? Uh, the, the direction as well as the value would have some perfect periodicity. Then it is called as a steady state current. You can have an analogy with respect to what the alternating current. Okay, so in all the three cases, that means steady state current, instantaneous current, as well as the steady current. So the conductor and which is carrying the current will remain the same. That means the cross sections will remain the same across different levels and different points in the conductor. Okay? So these things are very much essential in understanding the behavior of each of the materials. Can be a conductor, it can be a dielectric, or it can be an insulator. Okay, so what you have to understand here, so that is nothing but the composition of the current and its flow and its definition and also you should check whether it is nothing but whether it is following some of the laws or not. So, for example, you can say it is Ohm's law. So, Ohm's law follows or Ohm's law relates the external energy supplied, that is, applied voltage, and the electric current and the resistance. Okay, the relation is very simple and straightforward for the DC circuits, but not the electromagnetic circuits. Ohm's law is applicable for the DC circuits, not for the electromagnetic circuits, because the motion of the charges, because the motion of charges varies according to the medium. For example, the charges would behave differently in case of a liquid medium, in case of a gaseous medium, in case of dielectric mediums. So the charges present will pose different characteristics, and therefore the Ohm's law will not be sufficient to find the current through the different mediums, and hence, so we have to have some other concept such that which plays an important role in analyzing the electromagnetic principles. Okay, so for that case, so we have got one concept called as the current density. Concept called as current density. Very very important here. As I said, Ohm's law is not applicable to the electromagnetic engineering. Why? Because the charges movement will be different in different mediums. So as a result, the Ohm's law will not be sufficient to find current through such different mediums. So and hence you need to have one more concept. That concept is nothing but your current density. So Here in this chapter, we shall discuss more about the current density and the continuity equation and the properties of the conductors and dielectrics. Okay, and hence we shall extend this principles of current and current density to different materials. Okay, so firstly, we shall discuss about this current density. So that is given to be J vector. Okay? As you know, it is nothing but density means what it will be having both the magnitude as well as direction. So it is vector. So it is related to electric current. So it is nothing but it is defined as the current. It is defined as current per unit area. Current per unit area of cross section. Okay, unit area of cross section of an imaginary plane, okay, held normal to the direction of the current in a current carrying conductor. That means, so in order to find this current density, so what is that you need to have? So the first thing you need to have current flowing in a medium, and you need to find a cross section, and the cross section should be perpendicular to the direction of the current. So these things are very much essential in finding the current density. Okay, so the current density it can be defined at a point. So in field theory, in electromagnetic field theory, the analysis is primarily at a point in a field. Therefore, therefore we can use therefore we can use this concept of electric density, which simplifies our analysis in electromagnetics. Okay, so for this, by now we should be able to say what is current density is nothing but current per unit area, and that unit area has to be normal to the direction of the current. That means to select an cross section such that the current is flowing perpendicular to that area. Okay? So for that, just see this cross section of the conductor, for example, here. So let me assume this as the conductor here. Okay, and I'm having some current which is flowing like this, current which is flowing like this. So this is I, and this is also I here. And in this case, so I have to choose a small cross section here, small cross section here. Okay, and this cross section has to be perpendicular to the direction of the current. That means the current should flow like this in this direction. That means the to the surface, normal to the surface should be in line with the direction of the current. So this is nothing but a small cross section of area delta S, and this is point P. I am taking it as. So you can define the vector J here. You can define the vector J here. That is nothing but the current density here. Okay. So J you can write as the equation, that is delta I, change of current with respect to what small cross section, and that is as delta S tending to 0, small cross section, and you can also write this nothing but current crossing through the cross section of area. And the direction of J, it is same as direction of the current flow. Direction of J is same as the direction of the current flow. Okay, so therefore, so from this you can write Di as J vector into ds vector. Okay, so this is nothing but small current which is flowing through small cross section of area ds, so which is expressed in terms of the current density. If you wish to find the total current, so what you can do, you can integrate for the surface, that is nothing but di. Okay, so let us see that one also. So, so I just want to find. So I have equation like this. That is nothing but a vector into ds vector, I, so integrate the whole along the surface. Okay, so it is nothing but j vector into ds vector. So this equation is a general equation, so which does not require ds to be normal to the direction of the current. Okay, that means you can take another uh, surface like this. Okay, and the normal to the surface is like this. Okay, and the j vector, so it is like this, and this is nothing but delta s dash, and it's just p dash here. Okay, this surface, if you take this cross section, okay, so and the normal to surface is like this. Okay, and you can generalize using this one for any surface like this. Okay, so which is more suitable for any surface where the ds is not required to be normal to the direction of the current flow. Okay, so this is what the current density and the relationship between current and the current density. Okay, so what is the unit of current? That is nothing but coulombs per second, or it is amperes. It is generally it is known as amperes, but it is basically it is coulombs per second. And what is the unit of the current density? It is nothing but current per unit area. So it is nothing but amperes per meter square. Amperes per meter square. So this is the current density unit. Okay, and basically it is nothing but the dot product of the current density and the surface vector. Okay, yes. So what is that we have to make out from this discussion? So that means, so from a movement of charges, it constitutes current, and the current flow. So current flow, we just have to find out that what is the amount of current flow in a given medium. Okay, so to find the amount of current flow in a given medium, you require the concept of the current density, because the current density will be different at different points of the medium due to the arrangement of the free electrons in that cross-sectional area, and therefore the current density decides the amount of current flow in a given medium. The medium can be, again, I have said, it is conductor, dielectric, or any capacitance like that. Okay, for that matter. Okay, so we can extend this. We can extend this to relate this current density. Relate this current density to the volume charge density. So that is nothing but we have understood the volume charge density as rho v, and the current density is j vector. So we just have to have a relationship between these things, right? So this is volume charge density, and this is current density. So by now you should be able to distinguish between this volume charge density and this current density. So volume charge density is nothing but del Q by del P. Okay, and current density we have just discussed. It is nothing but current per unit area. That is nothing but J is equal to nothing but delta I by delta S. Okay, somehow you need to relate this and this. So let us derive that expression between the relationship between volume charge density and current charge density. Okay, so are you able to follow these discussions? So if you're able to follow these discussions, please type zero on the chat box. Or if you've got any doubts, please ask me. I'll give some time here, because these are theoretical concepts, so it should be understood. 2 minutes time I'll give. Please, if you have any doubts, you can ask me. Okay, so I assume that you are following the concepts. So now let us derive the relationship between the J and V. So as we have studied in the preceding sessions, that is the charged particles give rise to charge density. So that is nothing but rho v. So rho v, and this rho v is nothing but in volume, given volume. Okay, and current density is nothing but um, how much. If you want to relate this current density to the charge density, how much this um, volume charge is moving moving with a given medium, or passing through a given surface. That means you should know the volume of the charges which is crossing the given surface, then you can then you can relate those things. Okay, so volume of charges, you are given with, that is a rho v, and what is the rate of that volume of charge movement uh, through a given surface. So for example, if you are having a surface like this, okay, surface like this, and so I am interested in having a volume charge like this. I'm interested in having a volume charge like this. Okay, so this is my surface, yes, sir, and this is my charges in this small volume. Small volume. I'm interested in finding the movement of this charged particles. Movement of this charged particles. Okay, through this cross-sectional area. Through this cross-sectional area, such that I can get the current density. Okay, and this movement of this charge is nothing but it takes place with respect to some distance. Okay, so it can be what related to what time and the distance of the movement. So that is related to what the velocity, nothing but velocity. So it's nothing but distance with respect to time, displacement with respect to what, some time. So that is nothing but movement of this volume charge through this given surface. Okay, so that movement you can relate it to what the velocity vector. Okay, and hence you can relate it to what the current density vector. Okay, so for that case we shall take some axis of reference. Okay, so let me have a small volume like this. and small surface I'm taking like this, and this is the length. I'm interested in moving in x direction. I'm interested in moving volume element. This is the volume element moving in x direction. So the velocity of the element along x direction is nothing but Vx is nothing but delta x by delta t. So charge distribution in such a flow is treated to be what continuous, and the charge element of uh, volume delta V is covering a distance of delta x along x-axis in time t. Okay, so as t tending to zero, so you can denote Vx as what dx by dt. Okay, this is what the velocity vector associated with this small volume element, which is having some charges inside it and taking a small area in it, and the length is nothing but delta L. So this is the length which has been taken care along the x-axis. Okay, so what exactly is the volume here covered by this one in terms of surface and the length is nothing but delta S into delta L. Okay, so this is the volume uh, of the charge where what we are considering delta V is equal to delta S into L, and we can have a expression for rho V here nothing but delta Q by delta V. Okay, so from this, so we can write delta Q is equal to rho V into that is delta V, and electric current is nothing but delta I is delta Q by delta T. So I'll replace this delta Q by rho V into delta V by delta T. Okay, and I'll replace this delta V as in terms of the surface cross-sectional area and the length. So rho V into delta S into delta L by delta T. Okay, so if you apply limits as t tending to 0, okay, so it is nothing but di is equal to rho V into ds into dl by dt. So this dl by dt is nothing but vx. So rho V into ds into vx. Okay, so also we know that this di on the left hand side in terms of the uh, current density, that is j vector into ds vector. Okay, so j vector into ds vector. So this again on the right hand side, so the movement of charge is along the uh, x-axis. Okay, the movement of charge is along the x-axis. So what you can write, so this Vx into ds. So Vx into ds. So and this is nothing but rho v. So if you equate these things, so you will be getting this as j in terms of rho v into v vector. This v vector is nothing but your velocity vector. Okay, so if you just compare these two expressions on left hand side, right hand side, you will be writing in terms of what the velocity vector. Okay, so that is how the current density is related to what the charge density. Okay, so from this expression, you could observe the current density and the charge density is related by the velocity vector. So it is called as convention current density, convection current density. So because uh, it is analogous to the uh, heat transfer, heat transfer in the conductor. Okay, that is why it is called as convection current density. Okay, so by now what is that we have discussed? So we have discussed about what is electric current, what is instantaneous current, what is steady state current, what is current density, and so what is that the relationship between the current and the current density and the charge density. Okay, so this is linearly proportional. That is the convection current density is linearly proportional to the charge density. Okay, and the velocity with which the charge is transferred. Okay, so this is how the current movement or the charge movement takes place in any given medium. Okay, yes. So next, we should move on to one more concept that is called as the continuity equation. Continuity equation. So we know that the charges can neither be created, okay, neither be created nor be destroyed, neither be created nor be destroyed. Okay, so that means principle of conservation of energy. So in a given closed surface, in a given closed surface, the current I is related to the current density like this, given closed surface. That means current is flowing outwards from the closed surface. Okay, that means the current is nothing but movement of positive charges, flow of positive charges, and hence current is nothing but the outward flow of positive charges from the closed surface. So according to the principle of conservation of charges, there should be an equal amount of decrement in positive charge inside the closed surface. For example, if you take this as the closed surface, if you are assuming that there is a positive charge is flowing out of this closed surface, there should be an equal amount of charge decrement in the surface. That is minus q here. So that is nothing but the rate of if there is a rate of uh, charge, rate of increase of charge uh, happening outside the closed surface, the same amount of rate of decrease should be happening inside the closed surface. So this is nothing but the principle of conservation of charge. That means you can assume that so whenever there is a flow of charges taking place outside a closed surface, there is equal amount of decrease of a positive charge inside the closed surface. Okay, so the rate of decrease is denoted by minus dqi by dt, where qi indicates the charge within the closed surface. Therefore, you can equate this to what minus dqi by dt. So this is nothing but continuity equation, continuity equation of the current flow. Okay, so this you can relate to one more concept what we have studied uh, in the preceding lectures. So that is through what the divergence theorem. So if you apply divergence theorem here, okay, that means closed loop integral is equal to volume integral. Okay, so it is j vector into dv. So if you apply this divergence theorem, you convert surface integral to the form of volume integral, and if you simplify further, that is nothing but minus dqr by dt is equal to volume integral divergence of current density. So we'll relate this as minus of rho v with respect to what? Rho v with respect to dt. So this is nothing but point form of continuity expression, point form of continuity expression of the current. Okay. Yes. So why this discussion is done now? So this is nothing but so in any given material, you should not or you should assume that whatever charges movement is there, and that will be negated by the same amount of creation of charges or movement of charges. The same amount of charge takes place in order to meet the in order to follow the principle of conservation of charges. Okay, so this is how the current flow takes place in any given medium. Okay, if there is a rate of increase in the charge outside of the closed surface, there is equal amount of rate of decrease of charge inside the closed surface. So that can be obtained from this divergence theorem applied to the um, expression for the current. Okay. So if you got any doubts up to this point, you can ask me. I'll just leave it for 2 minutes. So if this is clear for you, please type 0 on the chat box. We can move on. So let us solve one problem here, and then we shall stop at this point, so that you'll understand how the current is flowing through a given cross section of the medium. Okay. Yes. Let us solve here. So find the current. Find the current crossing the portion of x is equal to 0, x is equal to 0 plane, defined by y is greater than or equal to minus 5 by 4, less than or equal to 5 by 4 meters, and z is greater than or equal to 0.01 and less than or equal to 0.01 meters. If j vector is equal to 100 cos 2y ax cap amperes per meter square. So the cross section is nothing but x is equal to 0 plane. X is equal to 0 plane. That means it is a YZ plane. YZ plane, and the range is given. The range is given Z. So you're supposed to find I. You're supposed to find I. What is the amount of I current which is flowing through this cross-sectional area? Okay. So just take down this details. You should solve this problem. Okay. Yes. So we shall take that Z, Y, X, and X equal to 0 plane. So this is a plane. Okay. So and it has to happen between this one minus pi by 4 to plus pi by 4 and plus 0 point 0.01 to minus 0.01. Okay. So minus pi by 4 plus pi by 4 and minus 0.01 plus 0.01. Simply an YZ plane. Okay. YZ plane. Yes. So I is equal to A vector into ds vector. So here ds vector or ds is what? Surface area. What is ds here? Hello? What is ds here? So what are the coordinates of this plane? I think you have forgotten it, right? So how to find this area? Length into breadth. So it is nothing but dy into dz, correct? Next, ds vector. So it has to be what? Normal to this one. So what is the normal to this plane? Which axis is normal to this plane? Yes, the normal to the plane is nothing but the x-axis. So dy into dz into ax cap. This is your ds vector. Okay, so let me solve this one. So I is equal to j vector into ds vector. J vector is given to you 100 into cos 2y into ax cap plus d vector ds vector, it is dy into dz into ax cap. So it is nothing but 100 into cos 2y dy into dz. So it is double integral, one for y and one for z, 100 into cos 2y dy dz, and apply the limits and get me the answer quickly.
So 2 amperes.
Yes, it is 2 amperes. 2 amperes is the right answer. So 100 is constant. Okay, cos 2y. Once you have to integrate with respect to y, and once you have to integrate with respect to z. Okay, so you just apply the limits, you will get the answers. So I is 2 amperes. So amount of current flowing through this plane is 2 amperes. Okay, so why the strength is less today? Sufrut?
Sir, he has gone to take the vaccine, sir.
Okay, is it available now? I think it has been cancelled now
Sir, from
today.
tomorrow it's suspended, sir. Till today, who have registered, they can take.
Okay, okay. I could not get the slot, and I read the news as it has been cancelled from. Okay, I missed it. Yes, why the strength is less? Early morning class. It should not happen. That is why I don't take class at 8:30. That too online. Why? Because some people still be still on the bed with their mobile logging into my class. These things will happen. That's why I try to avoid taking class at 8:30. That is online class. Hmm. And it has happened today also. And people still were logging in at 8:40 or 8:45 also. And I purposefully denied their entry. Okay, so it should not repeat. We should not be repeated in the next class. Clear? Yes. So I will just stop at this point, and I will resume my class at 11 o'clock today. Okay. Yes. You can exit. Thank you.
Thank you, sir.